Hello everyone, in this video I'm going to introduce to you 4 basic digital electronic components to create our design. Firstly, we got 1 bit multiplexer 4 to 1. Here we got 4 inputs and 2 sectors connected into 4 AND gates. Then output for multiplexer always 1 and connected with 4 gates. Second, we have 4 bits multiplexer 4 to 1 components. We also got 4 inputs and 2 sectors. Every outputs from each multiplexer are connected together and form one general output. Third, we have 1 bit full adder which have 2 inputs A and B and carry input C. A, B, C are going to connect with 2 XOR gates and 3 AND gates plus 1 OR gates. Hence, 2 outputs form S, which means sum, and C, which means count. Fourth, the ripple carry adder is a combination of pulse adder. At each stage of I, a full adder takes input A, B, C and produce output S and Ci plus 1. The carry out Ci plus 1 is used as input for the next stage. Then we have 4 bits register. So here we got D in 3.0, which means D for data load, and D in 3.0 is D0 inputs, D1, D2 and D3 inputs. Clock and reset are connected together into each register. Q is output. Q out 3.0 means Q0, Q1, Q2 and Q3 current input. This is 4-bit universal register. Okay, so to create the blocks diagram, we have 2 4-bit multiplexer are connected together into ALU, which consisting multiplexer, arithmetic units, and register, and connected all into 4-bit register. Then we are finished with our design.
The carry-in input K is set to 1 when the circuit functions as a 4-bit adder. Because the XOR operation with 0 does not modify the value B0 equals B, the B input flows through the XOR gates unaltered in this mode. For instance, the circuit executes a simple addition if A equals 1100, B equals 0000, and K equals 1. 1100 plus 0000 equals 1100. The output stays at 1100 because the final carryout is disregarded. This behavior corresponds to the timing diagram's procedure, where 1101 plus 0001 yields 1110. When the circuit is set up as a 4-bit subtractor, the 2's complement of B is produced by complementing the B input and setting the carry-in K to 0. The XOR gates, which invert B to its 1's counterpart, are first given the B inputs and K. For example, the XOR gates generate 1111 when A equals 1100, B equals 0000, and K equals 0. This essentially creates the 2's complement of B after taking into consideration the carry-in and the NOT gate. After that, the circuit calculates A plus B plus 1, which equals 1100 plus 1111 plus 1 is equal to 1100. This outcome is the same as subtracting a B equals 1100 0000 equals 1100. The time diagram shows the same process, where 1101 to 0001 generates 1100. The clock signal, CLK, is typically a square wave with distinct rising and falling edges. A positive edge-triggered D flip-flop ensures that the input value, D, is transferred to the output Q on the rising edge of the clock, regardless of the current state. The reset input, reset, operates as an active high signal clear signal, enabling the register to immediately force all D. flip-flops to 0 without waiting for a clock pulse and D inputs. This behavior aligns with